Okay, today we are together with the second online recitation, and we are going to deal with some problems related to ring theory. Uh, okay, any problem about the voice or about the connection? I think I managed the problem about the connection this week. I think you can hear me. If not, please write it on chat, and I can read them. Okay, at the same time. Okay. Let me start with my first question, and if you have any questions, please do not hesitate to interrupt me and ask your questions. I want these lectures to be interactive. This is a broadcast because I want you to ask your questions in case you need it while I'm solving the questions. Okay, let me first start with the first question. First, give an example. Give an example of a ring and a subring. Oops. Maybe it is better in this way. I don't know. Okay. And yes. And a subring of it. Subring of it such that the multiplicative identity of the ring is different from the multiplicative identity of the subring. Multiplicative identity of the subring. Do you think that it is possible? Huh? Is it possible? If you remember, in the group case, if we have a group, of course it has an identity, and all of its subgroups have the identity, and the identity of the subgroups is equal to the identity of the group, right? But in this case, in the case of rings, sometimes subrings may have different multiplicative identities, or even don't have multiplicative identities. For example, for this one, consider the ring. Consider R as what? Z10. Okay, this is nothing but Z10 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Integers modulo 10, and consider the subring generated by 2, okay, or namely 0, 2, 4, 6, and 8. Okay, this is a subring. As is a subring of R, Z10. But here, as you can see, 1 in Z10 is the multiplicative identity, right? Identity of Z10. But here in the subring, we don't have it, right? 1 is not in the ideal generated by 2. But even 1 is not in the subring generated by 2, this subring also has a multiplicative identity, which is 6. Consider the element 6 in S. The element 6 in S. Now let us apply the multiplication with all elements in S. 0 times 6 is equal to 6 times 0. 6 times 0, which is 0. 2 times 6 is equal to 6 times 2, which is equal to 2. 4 times 6 is equal to 6 times 4 is equal to 4. And 6 times 6 is equal to 36. And modulo 10 is 6, of course. It is 6. And lastly, 8 times 6, which is equal to 6 times 8, is equal to 8. And we apply the multiplication with 6 to all elements in S, right? So here, 6 is the multiplicative identity of the subring S, right? By these multiplications, we have shown that it is the identity, but as you can see, 6, but 6 is different from 1 in Z10. So with this example, you can see that we have a ring with the identity 1, and we have one of its subrings, S, which is generated by 2, and both have identities, multiplicative identities, but the multiplicative identities of the ring and the subring are different. Okay, so this may be the case in the rings. But if you're talking about additive identities, of course, additive identities has to be the same. Okay. Any questions? Any questions? No. Okay. Let me continue with my second question. Let R be a ring, and assume that whenever AB is equal to CA for some ABC in R, then we have one condition satisfied, which is B is equal to C. Okay, we have a ring something like this. We have some kind of cancellation, but from right and from the left at the same time. Then in this situation, we are going to prove that R is commutative. Prove that R is a commutative ring. Commutative ring. Okay, we are going to use this kind of cancellation to prove that our ring R is a commutative ring. Okay, so here, oops, we have something going on in one of the houses. Okay, now let X, Y. Let us take two arbitrary elements from our ring R. Okay, now we are going to show that xy is equal to yx. I'm going to mute all of you. Now mute here is just okay. I think okay. I muted all of you. Now we have taken two arbitrary elements of R, and we are going to show this identity xy is equal to yx. Commutative ring means that the multiplication here is commutative, right? So we have already known that our ring is an abelian group with respect to addition, and commutativity comes with multiplication. Okay, so using this identity here for our ring, if AB is equal to CA for all ABC in R, then we know that B is equal to C. We have some kind of cancellation here. Then under this condition, we are going to prove that our ring is commutative. So I have taken two arbitrary elements, x and y, and our aim is to show that xy is equal to yx. Okay, so for these elements, we have this identity, right? We already have yxy is equal to yxy, right? The same thing, the same multiplication, but using parentheses, we have y times x times y is equal to y times x times y, right? And what we have in the condition is that AB is equal to BC for ABC in R implies that no, not BC, but CA, implies that B is equal to C. So here, we have Y here, so we can consider these Y's as A in this condition, and XY and YX as B and C, right? So by using the assumption, we get xy is equal to yx. And since x and y are arbitrary elements, for all elements in R, we have the commutativity. So we are done. We are done. Yes. Okay, any problem? Any questions? No? Is everything okay? Okay. Then, continuing with the third question, let I and J be ideal of the ring R. Okay? Now, in the first part, we are going to show that I intersection J is an ideal of R. What you know about the ideals is that first we need a subset, then this subset must be closed under, this subset must be closed under addition, additive inverses, and the multiplication first to be a subring. And for the ideal, we need to have some kind of different multiplication from the ring. Okay, first, I is set to be an ideal. Let me use S. To say it's an ideal of R, first we need to show that it's the subring. Subring of R. And secondly, for this one, let me write it. For this one, we are going to show that x minus y is in S, or xy is in S. And secondly, we are going to show that x times y in S, or xy in S. And secondly, for the ideals, we are going to take an element from R and an element from S and show that x times, Yes. Can you see it? Okay, yes. R times x and x times R lies in S. Okay? First, we need subring, and then we need this elements in S. Okay? So for this one, I intersection J, we are going to use the fact that actually I and J are ideals of R. Okay? So let us take two elements. Okay? Let x, y be from I intersection J. I think last week we have shown that I intersection J is an ideal. I cannot remember exactly, but maybe we can show it again. Okay. Now we are going to show that. Show that x minus y lies in I intersection J first. Okay. Now, since x and y are elements from I intersection J, we know that x and y is in I, since we are taking these from the intersection, and x and y are from J. Okay, and from here, since x and y are from the ideal I, we know that x minus y is in I, x times y is in I, r times x, and x times r is in I. Why is that so? Because I is an ideal. And I is an ideal of R. Any problem with that? I just used the definition of ideal. Okay? And the same thing applies for J, of course, as xy is in J, and J is an ideal of R. We know that x minus y, x times y, and r times x, x times r are all in J for x, y in J, and no, we don't need that for R in R. Okay, so from the first one, we have x minus y in I, and from the second one, we have x minus I in J. This means that x minus y is in I intersection J. X times y is in I intersection J. No. Okay, we have a cat issue. And here, r times x is in I intersection J for every r in R, right? So we have shown that for two elements arbitrarily taken from the intersection here, and for an arbitrary element r from R, we have shown that the additive difference of these two elements lies in the intersection. The multiplication of these two lies in the intersection. And of course, here we should add x times r. X times r and r times x lies in the intersection, meaning that hence I intersection J is an ideal of R. Okay, we just show that all conditions of an ideal is satisfied for the intersection of these two ideals. Okay, so we have shown that I intersection J is an ideal of R. Under the condition, of course, I and J are ideals separately. Any questions? Okay, as the second part, we are going to show that for these two ideals, I plus J, which is defined to be R, no, not R. Let me call x plus y consisting of, no. Okay. This is just R plus x and s times y and r s from the ring R and x, y, x from I and y from J. Okay, this is an ideal of R. Okay, we are going to show this one right now. So here again, we are going to strongly make use of the fact that I and J are ideals. So let us first take two elements. I'm not sure whether it is true to write this in this way, or I think we should write something like this instead of this one. X plus y, such that x lies in I, y lies in J. But the other version is also true, of course, because since I is an ideal, all multiples of elements of I from with an element from R, from the ring R, also lies in our ideal. So the other version is also correct, but this is the, I think, the easiest way to see this ideal. So let us take two elements from here, x plus y, let's x plus y and x prime plus y prime be arbitrary in I plus j. And let us take one more element, r from R, to be able to show that just an ideal. So here First, we are going to show that I plus j is an ideal. X plus y minus x prime plus y prime. And this is nothing but we can use the fact that R is an abelian group with respect to addition. And we are going to write this as, of course, we are going to use associativity, of course. X plus y, get rid of the parentheses, minus x prime minus y prime, and we can write this one as x minus x prime plus y minus y prime, right? Because we know that R is an abelian group with respect to addition. Now, since x and x prime are from I, this means that this part lies in I. And since y and y prime is from j, this part, y minus y prime, lies in j, right? So we have an element of the form, the addition of two elements from I plus from an element from j. This means that this is from I plus j. Hence, I plus j is closed under addition and additive inverses. Now we are going to look at the multiplication. X plus y times x prime plus y prime. What we have is that you need to be careful about the multiplication because we don't know whether the multiplication is commutative or not. So you have to respect the order here. X times x prime plus x times y prime plus y times x prime plus y times y prime plus y times y prime. Okay. Now we are going to use the fact that I and j are ideals and subrings. Now here we have two elements from I. This means that this multiplication lies in I. And here these two are the easy ones. Y times y prime lies in I because y and y prime are from j. No, it lies in j because these two are coming from j. Now what can we say about these two elements? What can we say about these two? Now, x is an element from I, y prime is an element from j. And this means that actually you can see this element. Let me write this one separately. X times y prime. Consider x times y prime. We know that x is from I and y prime is from j. Okay? Now, since I is an ideal, and y prime can be considered as an arbitrary element from R, this means that x times y prime is an element of I, right? Of course, in the other way around, we can consider it as an element from j. And the same thing applies here for y times x prime. Similarly, y times x prime lies in I as y is an element from j, which is a subset of R, and x prime is an I. Okay? So what we have is that at the end, we have some kind of multiplication here, and these two, the addition of these two elements also lies in I. Okay? Because I, let me write the reasoning here, A as I is an ideal. Okay? So this whole part from the left lies in I, and this part lies in j, meaning that the product of these two elements from I plus j lies in I plus j. Okay? So the second condition is satisfied. These are the conditions for being a subring. And lastly, let us take this element again from I plus j and r from r, and we are going to consider r times x plus y. R times x plus y. This means that if we apply the multiplication here, r times x plus r times y, right? So if we consider r times x here, r is an element from ring R, arbitrary, x is an element from I. This means that this lies in I, as I is an ideal of R, and the second part lies in J, as J is an ideal. Okay, so we have an element from I plus an element from J, meaning that this R times X plus Y lies in I plus J. Okay, so it is something like closed under a multiplication by a ring element, meaning that hence I plus J is an ideal of R. Of course, under the condition that I and J are ideals of R. Okay? Any questions? Is everything clear about the ideal? Do you have any questions? No? Okay. Now, as the fourth question, is it really necessary? Okay, let me define some kind of special ideal. Okay, it is called the principal ideal generated by an element from R. Let me give this one as a definition. For A in R, of course, R is a ring. The set denoted by this one or this one, RA, consisting of all elements R times A, are running through all rings R, is called the principal ideal. Principal ideal generated by, again we have some add issue, okay, generated by the element A. Okay, you can show that these kind of sets are ideal. Please check. Check that this is an ideal. Ideal as an exercise. Now, with this definition, we are going to consider some ideals of sets. Consider the ring of integers, Z, and the ideals of Z, the ideals 6Z and 8Z of Z. Okay, I think in the lectures of your instructor, it has shown that all ideals of the ring of integers are of the form n times Z. Okay, and here in this question, we are taking two of them, 6Z and 8Z. Okay, these are principal ideals. No. Okay, these are principal ideals of Z, and as you can immediately guess, 6Z is generated by 6 and 8Z is generated by 8. Okay. Now here we have talked about the ideal generated by, no, not the ideal generated by this one, but the ideal. Okay, now consider the addition of these two. Okay, this is an ideal. We have shown it, which is an ideal. Ideal of Z. We have shown that in the previous question, right? Here, if we have two ideals, here, if we have two ideals, I and J, then we know that their addition, I plus J, is also an ideal. Here, we are considering two ideals, 6Z and 8Z of Z. So, and we know that all ideals of Z are principal. This is not shown in the lecture, but you can easily show it. Show. So what can we say about the generator of this ideal? What is the generator? What is the generator of 6Z plus 8Z? This is our question. Okay? Now 6Z plus 8Z consists of all elements of the form m times 6 or 6m plus 8n, where m and n are integers. Okay, so do you have any guess? Any guess for the generator? Nope. You don't have any? Okay. Actually, my guess for this one, once the generator is 2. Okay? Claim is that 6Z plus 8Z is generated by 2. This means that this ideal is nothing but 2Z. Okay? For this one, if our claim is that we are going to show two sides of the inclusion, now we are going to show that 2 lies in the ideal, this addition of ideal, 6Z plus 8Z. And for this one, it is very easy, since 6 is an element of 6Z and 8 is an element of 8Z. Then what we know that 8 minus 6, which is equal to 2. No. Okay. This, instead of 6 minus 8, let me write this one. Minus 6 lies in 6Z. So 6 plus minus 6, 8 plus minus 6 is equal to 2 lies in our ideal, 6Z plus 8Z, right? So 2 lies in our ideal means that the ideal generated by 2 lies in our ideal. So 2Z lies in 6Z plus 8Z. Okay? And for the other side of the equality, it is much more easier than the first one, since 6Z only contains some even integers. This means that 6Z lies in 2Z, as every element of 6Z is even. And similarly, 8Z lies in 2Z with the same reasoning, as every element of 6Z is even. Okay, this means that 6Z plus 8Z lies in 2Z. Combining this one and the first one we have found results, meaning that 6Z plus 8Z is nothing but the ideal generated by 2, which is 2Z. Okay, as you notice here, 2 is just the greatest common divisor of 6 and 8. Okay, and you can, yes, Sarhan. No, greatest common divisor. Yes, of course, greatest common divisor. So you can use this one actually for the integers and for some various rings, but for in our specific case, we just take actually the greatest common divisor of 6 and 8. Okay, and you can try as an exercise. Find a generator for 6z intersection 8z. Okay, of course the natural candidate for this one would be the least common multiple of 6 and 8. Okay, do you have any questions, any suggestions? No? Okay, let me continue with an easy question. Okay, what about the only ideals as another question? Okay, let R be a ring. R be a ring and I be an ideal of R. Okay? Now, our claim is that if I contains a unit, then prove that I has to be the whole ideal. Okay? We are going to prove this one, and then using this, we are going to show that the only ideals of a field are the trivial one and the field itself. Okay? Now, for this one, let me put a non-zero ideal, of course, here. Okay. Now, let us take an element, take a unit from this ideal. Let x be an element of I, which is a unit. We know the existence of such an element from the assumption of our question. Now, since I is an ideal, before that, now since I is an ideal, for every R in R times X and X times R lies in I. Now, so, and since X is a unit, what does it mean being a unit? Huh? Do you know the definition of a unit? No? Our first session will end in seconds, and we're going to continue after 10 minutes, okay? Since X is a unit, we know that there exists Y in R such that X times Y is equal to Y times X is equal to 1. And now for this element R, if we just take the multiplicative inverse of our element, this means that X times Y and Y times X lies in I. And this means that 1 lies in I. Okay, still continue. Okay, now this means that, yes, this means that 1, our multiplicative identity, lies in I. And for this one, what we have is that for any R in R times 1 and 1 times R. Okay, now where we left is that we are going to show that if an ideal I contains a unit that is an element of R which has a multiplicative inverse, if we have such an ideal containing a unit, then we are going to prove that this ideal should be the whole ring. Okay, now we'll be left with the thing that we have shown that the multiplicative identity lies in our ideal I, and then we are in the place of showing that the whole ring lies in I. Okay, now by using the fact that multiplicative identity is in I, by taking an arbitrary element from R here, R times 1 and 1 times R, which is equal to R, lies in I, as I is an ideal, and meaning that since this R is an arbitrary element, this means that as R is arbitrary, whole ring R is a subset of I, the ideal I. And we know that I is a subset of R, so I has to be equal to R. Okay, now using this one, we are going to prove the only ideals of a field F are the trivial ideal, the ideal generated by 0 containing or only the additive identity, and the field itself, and F. Okay? So, by the previous question, it is obvious. Okay? This was our aim actually. Do you have any questions? Now let me repeat this one. If we have a ring R and a non-zero ideal of R, and this ideal contains a unit, meaning that contains an element who has a multiplicative inverse, then our aim was to prove that this ideal has to be the whole ring. Okay, we have taken a unit element from I, and since I is an ideal, we know that for every R coming from the ring itself, R times X and X times R lies in I. Since X is the unit, we know that it has a multiplicative inverse. We call it by Y. And then we know that since X is the unit, X times Y is equal to Y times X is equal to the multiplicative identity of the ring R. So by using that I is an ideal, this X times Y or Y times X, which is actually equal to 1, lies in I. And then again, using the fact that I is an ideal, we have that for every ring element R, R times 1 and 1 times R, which are equal to R, lies in I, meaning that all elements from our ring R lies in the non-zero ideal I, and then we reach the conclusion that I is equal to R. And using this one, the only ideals of the field F are the trivial ideal and the field itself. Okay? Do you have any questions? No? Okay. Now let us continue with a question related to homomorphism. Okay? Now, as the question, let F from R to R prime be a ring homomorphism. As the first part, let I prime be an ideal of R prime, and I be just the preimage of this I prime. Be the preimage of the ideal I prime under the homomorphism F. Okay, this is just the preimage. We don't know whether F to the power -1 is a homomorphism or some map satisfying some special properties. We don't have them. This is just considering the set, the preimage of the ideal I prime. Okay, now our claim is that this preimage is an ideal of R. prove that I, which is F inverse of I prime, is an ideal of R. Okay, we are going to show this one. Do you have any suggestions? Under the homomorphism, the preimage of an ideal is an ideal. Okay, we are going to show this one. Now let us take two elements. We know the conditions that should be satisfied to show that a subset is an ideal. So let us take two elements. Let x, y be in I and R from R. Okay? Now first show that x minus y is in I, then x times y is in I, then r times x, x times r lies in I. We are going to show these three. So let us start. What can you say about x and y? Since they are preimages of something, this means that as xy is in I, which is f inverse of I prime, this means that f of x and f of y lies in I prime, right? This is very basic. So our aim is to show that x minus y, x times y, r times x, x times r lies in I. For this one, we are going to make use of the properties of the homomorphism, okay? So instead of x minus y, we are going to look at f of x minus f of y, okay? And this is nothing but f of x minus y. This is because f is a homomorphism, right? This is what being a homomorphism is, right? So this means that what we know is that, okay, what we have now, f of x minus y. Now, can we say that this is actually lying in I prime? Can we say that? Okay, of course we can say that because we know that f of x is in I prime, f of y is in I prime. So this means that this part lies in I prime. Why? Because I prime is a subring, right? As I prime is a subring. So this means that f of x minus y lies in I prime, and giving us that x minus y lies in the preimage of I prime, which is I. Okay, so I is closed under addition and additive inverses. Similarly, if we consider x times y and we apply f here, now what we have is that f of x times f of y. Again, the reasoning is that f is a homomorphism. Okay, now since f of x is from I prime, f of y is from I prime, this means that this part is an I prime, this part is an I prime, f of x times y is an I prime, giving us that x times y is an f inverse of I prime, which is I, and we have that I is closed under multiplication. And lastly, we are going to show that r times x, and x times r lies in I. We know that f of x is an I prime, right? So, so we consider the image of r times x. Similarly, you can do it for x times r. And using the fact that f is a homomorphism, f of r times f of x, Now this is an element from R prime, this is an element from I prime, meaning that this lies in I prime as I prime is an ideal. So R times X lies in the inverse image of I prime, which is I. Similarly, X times R lies in I. Okay, hence we have shown that, hence the preimage of an ideal under a homomorphism is an ideal. Okay, do you have any questions? Any suggestions? And now, here is the question, is it true that, the second part, is it true the preimage is an ideal? Is it true that the image of an ideal of R, let us use the same homomorphism and same rings, is an ideal of R prime? Okay, what do you think? The preimage is an ideal, but is it the case that the image of an ideal is an ideal? The answer for this one is no. Consider, not always, let me say, consider the injection F from Z to Q. Okay, these are rings. Z and Q are rings. And injection means that you're just taking an integer to an integer in Q. Okay, but here, for example, Z is an ideal of itself, right? Z is an ideal of itself. Now, F of Z is nothing but Z, right? Now, the question is that, is Z an ideal? Is Z an ideal of Q? Right? With the injection, the image of Z is Z under this injection homomorphism. And as a subset of Q, the integers is an ideal or not? The question is that. It is not. Z is not an ideal of Q. For this one, let us take, take an element from Z. Take, for example, 2 in Z, or any integer you like, and a rational number which is not an integer. And, for example, 1/3 from Q. Okay? If Z were an ideal, then this means that the product of these two elements should lie in Z, but this is not the case. But 2 times 1/3 is not in Z. This means that Z is not an ideal. Z is not an ideal. And that was the image of this injection homomorphism. So this means that the image of an ideal need not be an ideal. But we have one condition, that as the third part of our question, if our homomorphism from R to R prime is a surjective homomorphism, then prove that the image of an ideal is an ideal. We have this condition of surjectivity on the homomorphism F between rings R and R prime. Okay. Now let us take. Do you want me to leave this as an exercise, or you want me to do it right now? Any suggestion? If you want to try, I can just leave it as an exercise. Do you want it? Okay. Exercise. Yes, Serhan, thank you. Okay, I'll leave it as an exercise to you. Okay? And next week, if you have any questions related to this one, then we can go through. Moshina, any suggestion? Do you want me to do it? Huh? Okay, I think I'm leaving it as an exercise. No? Okay, exercise. I cannot hear any more comments on this one. You can just write it on the chat. No, okay, no other suggestions. Now, Jantal, exercise. Okay, thank you. But try it, please. At home, try it. You have many time to try something like this, so please try it. And if you have any questions or some way to solve this, if you need any help to solve this question, please send me an email, okay? Now, another question. Show that the ring 2z and 3z are not isomorphic. Okay. Now we have two rings, 2z and 3z, and we are going to show that they are not isomorphic. In terms of groups, we know that they are isomorphic groups. Okay, taking 2n to 3n makes them isomorphic, and this is a isomorphism between these two groups. But as rings, they're not isomorphic, and this is these homomorphism of groups fails because of the multiplication, of course. Okay, so we have to show that they are not isomorphic. Now assume that f from 2z to 3z is an isomorphism. Okay, now what we know is that, say, f of 2 is some 3n, okay, or some n in z. But what we have is that if you consider f of 4, you can write it in either the way 2 plus 2, f of 2 plus 2, or f of 4 as f times f of 2 times 2, right? And in this case, since f is a homomorphism, a ring isomorphism, f of 2 plus f of 2, which gives you as f of 2 is 3n, this is nothing but 6n. And from the second equality, we have f of 2 times f of 2, and we have 9n squared, right? So if these two rings were isomorphic, this means that these 6n and 9n squared should be equal. 9n should be equal to 6n should be equal to 9n squared. And from here, what we have is that 9n squared minus 6n is equal to 0. This is if and only if 3n parentheses 3n minus 2 is equal to 0. And from here, this is if and only if n is equal to 0 or n is equal to 2/3. 2/3 is not possible because n is an integer. This is not in Z, so this cannot be the case. Not the case. But what about n is equal to 0? Is it a possibility? N is equal to 0 is also not possible because we know that homomorphisms take additive identities to additive identity. F of 0 is equal to 0 always. But if n is equal to 0, since we have claimed at first that f of 2 is equal to 3n, this means that f of 2 is equal to 0, and this is equal to 0, which is not the case, right? So in each case, n is equal to 0, also not possible. So this means that our first assumption that f is an isomorphism between 2z and 3z is not correct. Hence, there is no isomorphism. Okay, there is no isomorphism between 2z and 3z. Okay? Any problem? So these two rings, 2z and 3z, are not isomorphic rings. Any problem? Any suggestion? Okay, now our very last question, and an easy one. You have to think about it. Now let R be an integral domain. What is an integral domain? Please think about it. And I be an ideal of R. Be an ideal of R is the quotient R over I an integral domain. You have seen in the lecture video of your instructor that an integral domain is a commutative ring with multiplicative identity and without any zero divisors. Okay, zero divisor means that you have a non-zero element and two non-zero elements multiplying to 0. Okay, we are calling such elements as zero divisors. An integral domain does not have such elements. Okay, now our question is that if you have an integral domain, you also learned about quotient rings. Okay, dividing a ring by an ideal. If you have an integral domain and an ideal of that integral domain, is the quotient an integral domain? Do you have any suggestions? Do you think that this is the case? This quotient is still an integral domain or not? Actually, the answer is, if there's no coming answers, the answer is no. R over I need not be an integral domain. Integral domain. If we say that, we have to give an example. Okay. Now let us take our ring R as, consider R as what? The simplest ring that we can imagine as ring of integers. Okay. And as the subring, as the ideal, and I as, for example, 10z. Okay, and if you consider the quotient R over I, this is nothing but z over 10z, and this ring contains all elements modulo 10, right? This is 0, 1, 2, blah, blah, 9, okay? But this one has zero divisors. Consider 2 and 5, which are non-zero elements. Take 2 and 5 from No, not this one, but this. From the quotient we are taking, of course. Take 2 plus 10z and 5 plus 10z from z over 10z, or you can use just modulo 2, the element 2 modulo 10 and the element 5 modulo 10. You can use each notation you like. And then if you consider the product of these two non-zero elements, 0 plus 10z is different from 2 plus 10z and 5 plus 10z. So these are two non-zero elements, but 2 plus 10z times, not addition, times 5 times 10z is nothing but 10 plus 10z, which is equal to 10z. This is 0 plus 10z. Okay, so we have two non-zero elements, and if we multiply these two, we get the zero of the ring, right? The zero of z over 10z. And this means that 2 plus 10z and 5 plus 10z are zero divisors in z over 10z, meaning that z over 10z is cannot be an integral domain. Is not an integral domain. So it is not true that the quotient of an integral domain is an integral domain. Okay? So these are all questions of mine for this online recitation. Do you have any questions related to the question we have solved? Please take a quick look on the questions. Let me start from the beginning. Okay, here. Here. Now this one about the ideals, the intersection, the addition of ideals, and we have a principal ideal generated by with a specific element, and we have the example related, the ideals again containing units, the field, and ring homomorphism. Do you have any questions? Is everything clear? Okay, if you don't have any questions or suggestions, hope to see you next week, okay? Please, if you have any questions, send me an email, or we can set a forum related to the video lectures and online recitations, then you can ask your questions there through Math367. Okay? See you next week.
Okay, see you.
See you. Thank you.